All right, so good morning, everybody. My name is Xinghan Lau. I am a graduate student in the Machine Learning Department at Carnegie Mellon University, and I'm here to talk to you today about some work that I've done jointly with my advisor, Roy Maxian, about clusters and markers for keystroke typing rhythms. So before I begin, I just want to have a quick thank you to Laser for inviting me here, to NSF for supporting this work, and also to David Banks from Duke University for his invaluable assistance in this work. So as a quick outline, what I'm going to talk about today, as kind of a brief introduction, what exactly is keystroke dynamics and what do I mean by clusters and markers? I'm then going to touch briefly on the data that we used for this work. And then the meat of the talk will be a three-step process that we used for identifying these clusters and markers. And finally, I'll touch on the demographics of the clusters, of the subjects and the clusters that we identified. So diving right into it, what exactly is keystroke dynamics? Keystroke dynamics is the study of typing rhythms. It appears to be unique to each person based on that person's physiology, behaviors, and habits. And there are many different applications for keystrokes, including computer security, emotion detection, and forensics. So in computer security, the canonical example is two-factor authentication. You have some adversary who's managed to steal your password, and you would still like to prevent that adversary from accessing your account. And so keystroke dynamics is the second factor in a two-factor authentication scheme where you're effectively saying, if you can't type my password like I do, you can't get into my account. In terms of emotion detection, a common use case for computer security would be detecting stress. So you imagine that you have some kind of insider who's trying to perpetrate some misdeed. While they're in the process of perpetrating that misdeed, they're likely to feel a great deal of stress. And if you can detect that stress, you might be able to take some actions that would mitigate the damage that they could deal. And finally, in terms of forensics, in my mind, this is kind of the after-the-fact part of computer security. In computer security, we're trying to prevent people from doing damage. In forensics, generally some damage has already been done, and we're now looking to try to identify some clues about who the culprit might have been. So when we talk about clusters and markers, I think it really helps to keep in mind blood types. So as we know, there's four common blood types. There's A, B, AB, and O. And these constitute four clusters in the population. And it turns out that blood types are determined by antigens, in particular the presence or absence of A and B antigens. If you have just the A antigen, you're type A blood. If you have just the B one, you're type B. If you have both, you're type AB. And if you have neither, you're type O. And the presence or absence of these antigens constitute markers for blood type. And they're markers for two reasons. First, they're simple, right? You're looking at two things. You can readily comprehend whether these things are present or absent. And it's also a perfect discriminator. As soon as I know what antigens you have in your blood, I know your blood type 100%. And it's critical here that you're able to, when you have a marker, you're able to determine the blood type of a person just by looking at his or her blood. You don't need to compare his blood to somebody else in the population, right? You just look at one person and you know that person's blood type. And so the way this work got started was that we posed a question of, well, are there analogous clusters and markers in keystroke dynamics? So to formally define this, at least for the purposes of this talk, when I talk about a cluster, I'm referring to a group of one or more typists that have similar typing rhythms. And I'll leave the definition of similar up to the researcher. And there's a particular definition I'll use for this work that you'll see in a couple of minutes. When I talk about a marker, what I mean is some simple attribute of the data that cleanly discriminates a cluster from the remainder of the population. So it's critical that it is both simple so that you can readily understand it, and it's important that it perfectly discriminates the population. So an example of such a marker might be, for a particular cluster, that the average latency time of all subjects in this cluster is greater than 1 second. So that is, the average time between key presses is greater than 1 second. This is obviously simple. You can calculate it using just that person's data. And if it is a marker, then it has to be a perfect discriminator. So you might ask, well, what's so great about having these clusters and markers, right? Why do we care? So there's a couple of reasons. So first, it can greatly aid us in forensics by allowing us to rule in or out large chunks of the population. So if you go back to the blood type analogy, if you think about going to a murder scene, the police might say something like, well, we know the murderer has type A blood. Well, when they're looking for suspects, they can immediately rule out anybody that doesn't have type A blood. Having these clusters and markers will also allow us to do more efficient research. We can focus on a single cluster at a time. Right now, we're in a position where we try to apply our techniques across the entire population, as though the entire population was the same. And that's not the case. So if you can focus on a particular cluster at a time, you can look for specific techniques that work well for just that cluster, and then find some other technique that works works well for some other cluster. And then at the end of the day, you can figure out what overarching scheme might work well for the whole population. And along those lines, we can develop better algorithms for authentication just by acknowledging that we have these different clusters. It's probably not surprising that different clusters will have different algorithms that work better for the people in that cluster. So you necessarily improve performance if you just look at a single cluster at a time, use the best algorithm for that particular cluster, and then repeat that process for the whole population. And the fact that you have a marker allows you to immediately determine which cluster a person belongs into, so you can actually pull this off. So I've posed a question that is multi-part and a little vague, right? Do clusters and markers exist for typing rhythms? So now I'm going to try to break this down into 3 questions, and then there'll be sort of a meta question at the end. So the first question is whether or not there are clusters of typing rhythms. The second is what are the distinguishing features for each cluster? And I'll make the distinction here between distinguishing feature and marker by saying that a distinguishing feature is anything that characterizes the subjects in the cluster, but it does not necessarily have to perfectly discriminate the subjects in the cluster from the remainder of the population. There can also be very many distinguishing features. It's not difficult to imagine that there might be a dozen or 2 dozen or 3 dozen keystroke features that are characteristic of typists in a particular cluster. The third question will be, well, given that we have a long list of these distinguishing features, can we distill them down into the simple marker that we're looking for? And finally, our meta question is, well, given that we have these subjects that are in the same cluster, we know that their typing has to be similar, but do they also share similarities in their demographics? So to give you a little foreshadowing of the results, since I'm up here, you probably guessed that yes, there are in fact clusters of typing rhythms, and I'll show results for 2 of them today. As for distinguishing features, there are quite a few. And for the clusters I'll talk about, these are extreme hold and latency times. So the hold time is how long you hold down a particular key when you type. The latency time is the time between key presses. And finally, for distinguishing features, for distilling distinguishing features into markers, we can do so, and in fact, we can get a single threshold score, which will constitute the marker for each cluster. As for the demographics, yes, there's also similarities there. In fact, one of the clusters that I'll talk about today consists of only women. So a little forewarning here that this is intended as a proof of concept work. I'm not making any claims about generalizability. I'm just saying that the techniques I used happen to work on this particular data set that I'm looking at. Which brings me to the data. So for this work, we decided to use the strong data set, and this is a previously collected data set that is publicly available. It consists of 51 subjects, each of whom have provided 400 repetitions of a password, and this is done in 8 sessions of 50 repetitions each. The password, which is intended to mimic a strong password, and hence the data set's name, is period TIE 5 capital ROANL followed by the return key. Each repetition consists of 11 hold times and 10 key up, key down latency times. And a key up, key down latency is just the time between when a key comes up and when the next key goes back down. The advantage of using this data set is that there was an external timer used to collect the data. And so the timestamps are accurate to within 200 microseconds, which is much better than what you can typically get if you just go through the operating system. However, despite having these 400 repetitions, we're only using the data from session 8, and this is the 8th and final session. And the reason for this is that this is the most practiced data that we have from the subject. So if you look at the curve at the bottom of the screen here, This is what we call a practice curve. Along the x-axis is the repetition number from 1 to 400. Along the y-axis is the time that it takes someone to type a password. The red dots here are how long each repetition takes to type, and you can see that I fitted a curve here, which has a nice exponential look. And so the issue is that as somebody types a password more and more often, and you've probably encountered this yourself, right, when you have a new password, at the beginning you're getting a lot better at typing the password, and eventually you plateau in your performance, if you will, right? You don't change very much between successive repetitions. And so the reason that we're using only the 8th and final session is that our interest here is in the subject's typing rhythms. We're not interested in how these typing rhythms are changing with practice. If we were to use all of the data that we have available to us, we risk confounding our experiment by capturing practice effects and potentially finding markers for practice instead of markers for what we're actually interested in. So that brings me to the first part. Are there clusters of typing rhythms? So you remember that our goal is to cluster our subjects. And it would be a bit confusing to directly cluster the repetitions that these subjects produce, because we might have a case where we have 50 repetitions from each person, 25 end up in cluster A, 25 end up in cluster B, and now which cluster does this subject belong to? So to avoid this phenomenon, what we're going to do instead is we're going to summarize each subject by a single median vector, and I'll describe what that is in a moment. But this median vector is going to act as an exemplar for the subject. And by clustering the median vectors instead of the raw repetitions, we'll end up clustering the subjects. So what is a median vector? So you imagine that you have some nice keystroke data. So for us, for a single subject, we would have 50 rows in this table because we have 50 repetitions. We have a bunch of hold times and we have a bunch of latency times. The hold times are on the left and they're indicated by the prefix, the capital H prefix. The latency times are on the right and they're indicated by a prefix of UD, which stands for key up, key down. So all we do to compute the median vector is by column here, we just take the median. And this gives us a single vector out at the end of the day, which has the same dimensionality as the original data. And this outputted median vector now acts as the exemplar for this subject. So I've talked quite a bit about clustering already, and so you might anticipate that I'm about to tell you I did something like k-means to find some clusters. For those of you who might not be familiar with sort of machine learning techniques, k-means is a classical clustering algorithm, which basically picks k cluster centers, and then it assigns each subject to the closest center. And we're not going to use k-means or an algorithm like that for two reasons. So the first is that using k-means or anything like it requires a prior knowledge of k, that is the number of clusters in the data. This would be kind of like asking a researcher working on blood, well, how many blood types are there? But you can't look at anybody's blood before you answer that question. Right? It's kind of an impossible task. There could be 2 clusters. There could be 2,000. We just don't know. The second reason is we don't want a hard clustering. So what k-means gives you is it says, well, this subject belongs to this cluster, and that's it. That's all you get. But what we're more interested in, we'd also like to know, how it is that the subjects within a cluster are related, and also how subjects in different clusters are related, right? Are clusters homogeneous, or are there sort of distinct subclusters within them? If we're looking at subjects in different clusters, are they a little different, or are they vastly different? So what we're going to use instead is a technique called Agnes clustering. And this stands for agglomerative nesting clustering. It's an example of a hierarchical clustering algorithm. And there's 4 steps to this algorithm. It's pretty straightforward. There's an initialization step where you start with 51 clusters, and that's because we have 51 subjects. Then we iterate. At each iteration, we're going to compute the similarity between all pairs of clusters. And the similarity is going to be defined here as the average Manhattan distance between all pairs of objects in the clusters. So just to give you a quick example, let's say we have 2 clusters, A and B. Cluster A has subject 1 and subject 2. Cluster B has subject 3. Well, we have 2 pairs of objects here, right? The pair of 1 and 3 and the pair of 2 and 3. So to compute the similarity, we just compute the Manhattan distance between 1 and 3, and the Manhattan distance between 2 and 3, and we take the average. Once we've identified these similarities, what we do is we just merge the two most similar clusters. And we're going to rinse and repeat until we have only a single cluster left. And this cluster will consist of the entire population. So what do we get when we apply this technique to the strong data set? Well, the easiest way to visualize the result is as a dendrogram. So if you're not familiar with one, how you read it is along the x-axis, you have the different subjects. The coloring I'll get to in a second. Along the y-axis, you have height, which is kind of this arbitrary measure. And it's used mostly in a relative sense to say whether things are more similar or less similar. The similarity of any two subjects is defined by the height of the first common junction. So hopefully my laser pointer will work. So if you have, for example, subject 2 and subject 20 here, the first common junction is this point right here. And that has a height of, I don't know, roughly 18, let's say. So these two subjects are relatively similar. If you pick, say, subject 2 and subject 40 here, the first common junction is going to be up here, which has a height of maybe 30. So 2 and 40 are more dissimilar than 2 and 20. If you go to the extreme and you take subject 2 and subject 36, who's up here in the upper right, the first common junction is actually this root junction here. And by definition, that's the highest height, and thus subject 2 and subject 36 are vastly dissimilar. So, did you have a...
Yeah, I was just wondering if you could speak a little bit to why 36 was an outlier in this, if that
I will get to that. Yes.
Excellent.
That'll be at the end when I talk about the demographics. Cool. Yeah. So, for the purposes of this talk, I'm going to focus on two clusters. So there's the subject 36 cluster, which is in blue in the upper right, and this is the singleton cluster that just contains subject 36. There's the women cluster, which is in red, and it turns out, well, by its name, that you might guess that these are all women in this cluster. And there are also a couple of other clusters that you can identify here, but that I just don't have time to talk about today. So there's a sort of a cluster here to the right, and there's kind of a big cluster here in the middle, which seems to be, everybody else. So having identified the clusters, the next question to ask is, well, what is it that distinguishes each cluster? So to do this, we're going to use something called sparse logistic regression. It takes as input repetitions from subjects in the cluster, but also repetitions from the remaining subjects not in the cluster. So you're actually going to use all of the data that you have available to you. The output is going to be a list of distinguishing features, ranked from most important to least important. And the way that importance is going to be conveyed by the algorithm is it's going to output a set of weights. The most distinguishing features will have the largest magnitude weights. And I'll pause here to mention that typically, prediction is the goal for logistic regression. We're trying to predict, usually, what, given a particular repetition, does it belong to somebody in the cluster or somebody not in the cluster? But for the purposes of this work, we're actually more interested in the weights, because it'll turn out, as you'll see in a couple of slides, the weights are what determine the predictions. So what we're interested in here is, why do we make the prediction that we do? Because that will tell us which of the features that we have distinguish this cluster from the remainder of the population. So to describe what sparse logistic regression is doing, to give you a little bit of confidence that these weights are doing what I say they're doing, I'm going to need a little bit of the notation. So I'm going to denote a repetition by this bold-faced X. And this will be a 21-dimensional vector, because I have 11 hold times and 10 latency times concatenated together. I'll denote weights by a bold-faced W. This will also be a 21-dimensional vector, because I'll have one weight per keystroke feature. And it's critical that you understand the weights are chosen by the sparse logistic regression algorithm. These are not things that I input in. These weights are learned based on the data that you feed in. The heart of sparse logistic regression is a linear score. And if you're familiar with the notation, it's just the dot product between W and X. If you're not familiar with that, you can just think of it as the sum, where each term in the sum is a weight multiplied by the corresponding feature. Once you have this score, you can apply the logistic function to turn the score into a probability. And this will be the probability that a repetition belongs to a subject in the cluster. So here we have the score that was on the previous page. And there's also the formula for the logistic function, which happens to be 1 over 1 plus e to the minus x. And when you plot that function, it looks like the graph on the right. So what you can see that the logistic function is doing is it's converting any real valued score to a value between 0 and 1, which we're then interpreting as this probability that a repetition belongs to somebody in the cluster. And the score actually completely determines what the prediction is going to be. So you can see if the score is very negative, it's going to be very highly unlikely that this repetition belongs to somebody in the cluster. On the other hand, if the score is very positive, it's highly likely to belong to somebody in the cluster. So the score is effectively determining what the prediction is going to be. But now if we look at the form of the score, it's this nice linear combination. And if you imagine that you have a weight that is very, 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 very large, well, that corresponding term is going to dominate the score. If it dominates the score, it's going to dominate the prediction. And what that means is, if you have a feature that has a very, very large weight, that feature is basically going to completely determine what your prediction is going to be. That is, it is highly distinguishing of the typing from subjects in the cluster. And to take this in a slightly more general sense, the larger the magnitude of the weight, the more distinguishing the feature is going to be. So we can run this for the clusters that we identified, the 36 cluster and the woman cluster. And we can get out two nice tables like this. So you have the index from 1 to 21. You have the feature. Again, the prefix of capital H means it's a hold time. The prefix of UD means it's a latency time. You have the actual weight. And then you have what I'm calling the normalized weight. And the reason that normalization has to be done here is because latency times are typically an order of magnitude larger than hold times. So to keep everything on kind of even footing, we normalize by dividing through the weights by the standard deviation of the corresponding feature. So if you look at this table, let's start with the one on the left, you can see that, oh, I should mention one more thing, that these tables are ordered by the magnitude of the normalized weight, from largest to smallest. So if you look at the 36 table, what you can see is that, well, the most important feature is the hold time on the capital R, right? And then there's some hold time on A, hold time on N, then some latency, another hold time, more latencies, right? So we're seeing that there's quite a few features that matter, that are distinguishing about subjects 36's typing. It's not as though there is only a single feature that's important. There are features that are unimportant, which are those starting after position 15, because these have zero weight. Right? They don't contribute to the score whatsoever, and so they don't influence your predictions. If we look at the right-hand side table, we see a little bit more order than on the left. So the 11 hold times occupy the top 11 spots in the table. And what that tells us is that these 11 hold times are the most distinguishing features of the women cluster. The latencies, however, still matter, because while they might occupy the bottom 10 spots of the table, they still have non-zero weight. So they're at least somewhat distinguishing of typing from subjects in the woman cluster. But if you look at this table, you'd be hard-pressed to tell me what the marker is, what is it about the typing of either of these clusters that sets them apart from the remainder of the population. So the next step will be to distill these features into markers for each cluster. Before that, yeah.
Yeah, so you said that you were using...
I think we want the microphone.
Hi.
Yeah.
So you said you were using sparse logistic regression.
Yes.
And what you described was just logistic regression. So what was the sparsity part of that?
The sparse logistic, so in logistic, so technically speaking, the difference is the addition of a penalty. And the penalty basically encourages the algorithm to pick zero weights where possible.
So this is like a lasso penalty?
It is a lasso penalty, yes. It's an L1 penalty. So the reason that we use a sparse logistic regression is that you end up with these actual zero weights, which tells you, hey, these are the features that are not important at all. They're not at all distinguishing. If you were to run just standard logistic regression, you would end up with the remaining entries being very small but non-zero in value, and it would be hard to distinguish which were unimportant and which were important. All right. So step 3, distilling these distinguishing features down into markers. So to do so, I'm going to introduce the concept of hold and latency time rankings. So there's 2 clusters, 36 and women, and they seem to be identified by collective hold time behavior and collective latency time behavior. And so what I want to do is I want to summarize the hold time behavior into a single number, and then I want to do the same for the latency time behavior. So what I'm going to do is, for each hold time, I'm going to take the median value for each subject. So I'm going to have 51 median values, 1 for each person. Then I'm going to rank order the subjects by this median value, from slowest, which will be number 1, to fastest, 51. For each subject, I'm then going to have 11 of these rankings for the hold times. And I'm going to take the average, and this will be the average hold time ranking. I'm then going to repeat this procedure for the latencies. So to give you a little visualization, let's say I have 3 subjects and 2 keystroke features. Say my first keystroke feature is the hold time on period. I rank order my subjects 1, 2, 3, and maybe it comes out ABC. I look at the hold time on T, which is my other keystroke feature. I rank order again 1, 2, 3, and this time it comes up BCA. Then all I have to do is I take the average, and I can see that, well, subject B is in position 1 with an average ranking of 1.5. Then it's A with ranking 2, and then C with ranking 2.5. So if we apply this to the clusters that we identified, we get partial success. So let me describe what you're looking at here. So on the left, you have a hold time ranking table. On the right, you have a latency time ranking table. Both the tables also have the position of the subject, and I've also included the median, hold, and latency times. And this is just for your reference, just to give you a feel for what timings correspond to a particular ranking. So I've indicated 36 here on these 2 tables with a blue dot. And you can actually see that 36 is perfectly separated. In fact, there are 2 example markers I could choose. So on the hold time ranking on the left, I could say, well, to be in the 36 cluster, you have to have a average hold ranking of greater than 49. And you can see that draws a line in the sand that perfectly discriminates 36 from the remainder of the population. Alternatively, I could pick the latency rankings and say, well, the latency ranking has to be less than 3. Again, you can easily verify that only 36 has a latency ranking less than 3, and everybody else has a ranking greater than 3. But now, if we look at the women cluster, well, we don't have quite the same level of success. We have almost success. So the subjects in the women cluster are indicated both in bold here and with the red dot. And you can see that when we look at the hold times, there's a little wrench in the mix, which is subject 11. So subject 11 is not part of the cluster, but there's no way to exclude 11 from the cluster while also including 30. So I can't find a perfect discriminator. And if I look at the latencies, even though these rows are adjacent in the table, if you look at the actual position numbers, they're scattered all over the place. So I don't quite have the success I wanted. So if we look back at these weights that we identified, you'll recall that I said, well, the hold times are definitely the most distinguishing features. But the latencies also are somewhat distinguishing, right, for the women cluster. And so the thought was, well, maybe we can combine these 2 pieces of information, combine the hold time rankings and the latency time rankings, generate a combined ranking, and in this combined ranking, I can find the marker that I want. To do so, I'm going to employ a support vector machine. And I'm going to do that because I'm going to insist that my combined ranking be linear, just because that will make it easy to interpret, and I'll understand what's going on. So my combined ranking is going to be some coefficient A times the hold time ranking, added to some coefficient B times the latency time ranking. I would like that the woman cluster be perfectly separated in this combined ranking. And as it turns out, there might be very many values of A and B that will do the job. And so I need to express some preference about which values of A and B I'd like. So what I'm going to say is, I would like to choose A and B such that I have the largest margin possible. And the margin is the distance between sort of the last member in the cluster and the first member not in the cluster. As it turns out, support vector machines were designed to solve exactly this problem. So I'm going to use one. I'm not going to go into the details of how exactly a support vector machine works because I don't think it would add anything. But I hope you'll trust me that it will take as input the hold time rankings and the latency time rankings, and it will output two values, A and B. And in our case, for the women cluster, we get these values of A and B. 0.97 for A, 0.23 for B. We can compute the combined ranking based on this, and that's actually what you see in the table. So you see from left to right, you have the position, you have the subject, you have the hold time ranking and the latency time ranking, which you already saw. And now you have a column that indicates whether or not the subject was in the cluster, the women cluster. And then finally, the combined ranking, which is computed according to the formula. And what you'll see here is now we have success. The women cluster is perfectly separated from the remainder of the population. If I pick a threshold at, say, 17, all of the members of the women cluster have a ranking less than 17, a combined ranking less than 17. And the remainder of the population has a combined ranking greater than 17. So now that we've identified these clusters and their corresponding markers, it's sort of interesting to ask, well, as Nate pointed out, right, we saw that 36 was so different, right? And it sort of begs the question, well, are these clusters in general somehow, unique in their demographics? So I'll return to this dendrogram that we saw earlier. So it turns out that subject 36 has temporal lobe epilepsy. This is a relatively rare condition, and it's not a condition that anybody else in our subject pool suffers from. And so we think this is affecting his typing in a way to make him so distinct from the remainder of the population. I mentioned that the cluster here in red is a cluster of all women. And we actually did a chi-square test to see if it was just by chance or not. And it turns out that it's highly unlikely to be due to chance. The p-value here is less than 0.005. But unfortunately, there are also women that are scattered amongst the black labels here. So there's not a perfect correspondence between membership in this cluster and being a woman. And we searched through the rest of our demographic information to look for anything that might explain it, but unfortunately we weren't able to find anything. So this is still a bit of an open question. Brings me to limitations and future work. So again, I'll remind you, this is proof of concept only. Right? There's the generalizability of these techniques is unknown. What needs to be done to generate this generalizability is to evaluate these techniques on more data sets, and ideally larger ones. I'd also like to be able to correlate clusters with specific typing behaviors. So for example, it would be interesting to say, just making up a story, well, the women cluster are all in this cluster together because they have the unusual habit of striking the space bar with their left index finger. That tells us something about the actual behavior of the typist that's causing them to be grouped together. And finally, as sort of a more far-looking question, right, can we use these techniques for arbitrary free text? So what I've described here today is mainly intended to work in a situation where you're seeing multiple repetitions of the same password over and over again. But there's a question of how exactly do we extend these techniques when people might type anything at all? Finally, takeaway points. So first, yes, there are clusters of typing rhythms. Second, it is possible to identify features that distinguish members of these clusters from the remainder of the population. These features can be distilled down into markers, and that allows us to immediately determine which cluster a typist belongs in. And finally, our demographic analysis shows that there's at least some structure to these clusters. So with that, I will thank you very much for being so attentive. And we'll move to questions.
I didn't hear it, maybe I missed it. Was the testing done on physical keyboards or soft keys?
We're using physical keyboards here.
Would it make a difference? Would the results be transportable?
So the question of it's a general question in keystroke dynamics of whether or not you can transport results between hard physical keyboards and I guess touch screens is what you're referring to as soft keyboards. So that's not known at the moment. And this is true for almost all results in keystroke dynamics.
What demographics do you know about for subjects? I mean, you clearly know their gender and you know that one of them has temporal lobe epilepsy.
Yeah.
Do you know age? Do you know whether they
Yes.
have formal training in touch typing? Do you know what they do for occupations? Are any of those possible clues to the women who are not in your women cluster?
So I can't list off every single demographic piece of information we have because the survey is, Roy, you can correct me if I'm wrong, I think it's about a 5 or 6 page survey. So amongst this is age, gender, handedness, whether or not you play musical instruments, what your occupation is, how many hours a day do you spend on various keyboarding activities. Yeah, there's a long, lengthy list of things. And I can tell you offline what those are because I can dig up the survey that we used. But yeah, even whether or not you speak other languages is in there. What style of keyboard you like and so on.
Quick question. So we have knowledge now that we have, as you said, the clusters exist. There are markers. Obviously, there are certain characteristics to those in terms of how well we can differentiate between populations. Given the preliminary study, do you see certain systems based on the evidence that you received from the study that would find this useful?
So as far as I know, there are actually very few working and vetted keystroke dynamic systems. I would go as far as to say there's probably 0. As for what kind of system could leverage this information, if you eventually intend to transfer keystroke dynamics out of sort of the proof of concept stage that it's currently in into a working product that you can deploy somewhere, one of the things that you're going to have to be worried about is speed. Right? You can't take 5 days to detect whether or not somebody should have access to the account or to know what their characteristics are. It's just too slow. And so by having these clusters and by having these markers, you're able to very quickly determine at least which other tests you need to run before you can validate the identity of the person.
Great talk and very interesting work. Could you go back to slide 30?
30, sure. Well, that's was it this one that you're looking at, or
no,
this one?
Yes, exactly.
Yeah.
So in the theme of the workshop, providing constructive feedback,
Yeah.
You had a lot of these tables in your talk, and I couldn't figure out on any of the tables what was the main points I've been looking at. So generic advice I have been gotten is that people tend to like numbers and tables, but try to do more that gets the message point. So I sometimes do this my well, and I get told about it later that from senior people, I was sleeping in your talk because you were showing this. So I think you were doing very interesting work, but for most of the tables, I couldn't get what was the point. So for example, the next slide you have 31.
Yeah.
So yes, so this is visualization when I could actually understand when somebody was saying that, okay, here's outlier, etc. So
well, so certainly for this table, I apologize if it wasn't clear. So the only point I was trying to make here is that I have perfect separation, right? That I can separate the people in the cluster from the people not in the cluster. That was the only message here.
Well, see, there's no need to apologize. The generic point is that with topic of theme, doing science also, how do you communicate it? And tables don't communicate it very well in a talk, so you would want to have graphs or such, and that would give like takeaways that I can later remember and visualize. So that's my only point.
We had an online question.
Yep, sure.
Yes, two quick questions from Thomas Edgar, who is online. First question is there an assumption that typing behavior is consistent over time?
So I've already talked about the fact that there is practice. So no, typing behavior is not the same over time because it changes with practice.
And the second question would be, would you expect these clusters to be reproduced by the same population with another data set collected today?
So that's an interesting question, and this is certainly one of the areas of generalizability that I would like to explore. So the question of whether or not the same subjects typing different things would produce the same clusters, if you're talking about a fixed text, especially something like a password, where people tend to have very distinctive ways of typing that password, I would be less confident about saying that these clusters are likely to remain constant if I change what the text being typed is. However, as a general comment, if we're taking, say, free text, I would expect those to stay roughly the same, barring any, very unusual changes in the stimulus item.
So at the beginning, you talked about for markers, you want a marker that you can look at one person without reference to the rest of the population, like blood type.
Yeah.
But I think, from what I understood with your rankings, you did these old length rankings and latency rankings. And that ranking does depend on the rest of the population. So your marker depends on how big the population is, how everyone else typed. So how would you extend this to like what your original marker would be?
So, so what you can do for a new person is you can effectively treat the data set that we've collected, or any data set that you collected, as a baseline. And so what you can do is you can bring in a new subject, and based on only that person's data, you can compute the median vector for that subject. And then when you do this rank ordering, all you're going to do is you're going to rank order them in with all the other subjects, right? So if it's between, say, I have 5 subjects here, right? The new subject comes in between C and D, I give them a rank of 3.5, right? Or I could even do something fancier and do some kind of linear interpolation between C and D. And so that would give me the ability to compute the ranking for that subject. And once I have that, I can compute the combined ranking and I can assess whether or not the marker holds or not.
I'd like to talk about the scientific method with respect to what you did here, and the first step of that, which is framing the problem, which is maybe the least scientific part of the scientific method. But could you just describe sort of, some people have said framing the problem is half of the solution, right? Could you just describe the process of the inspiration for the hypothesis? Is this in a family of 50 hypotheses, and this is 1/50th of the things you're pursuing towards the goal of work drive, whatever the vision is, right, of what's driving, the hypothesis part of the method?
Yeah, so the inspiration here was, do we have clusters of some sort, right? Is there some structure to keystroke data that hasn't yet been established? Because as I pointed out in my talk, one of the things that keystroke researchers tend to do is they say, well, everybody must be the same. We'll treat everybody identically. And so for me, there was a question of, well, is there some kind of organization here in the data that we're missing out on? Because knowing that there is this organization will allow us to do something based on that organization. As for framing the problem, I guess this was the way that we tried to frame it, to say, well, first of all, are there these clusters at all, right? That's the first, most obvious step. And then maybe the not quite so obvious step is to establish what distinguishes these clusters, as opposed to trying to jump directly to a marker. And I would say that the reason we did that is a little bit because of the tools that we had available to us, but also because, just because we identify something as a marker doesn't mean that there's not other things about that cluster that are also interesting. They may not be completely unique to that cluster, but they're interesting nonetheless. And so that's why we have this intermediate step between, okay, well, are there these distinguishing features, and now can we distill this down into a marker?
Right. So for data, is there any explanation on you pick median over other metrics for each subject, or did I miss the part?
So I used the median because to use the mean, which would be the other choice, would expose me to outliers. And in keystroke data, outliers are a common problem because people will do things like sneeze while they're typing. And so now you have a 5-second latency time that is highly unusual, and you don't necessarily want to give much weight to that. So I use the median as a robust metric.
So I'm curious about your subject 36, your singleton in there. When I saw the original data, which just had little circles in it, can you go back to that slide easily?
Let's see, what you're talking about.
One of the very first, that was the one right there.
Yeah.
Yeah. I'm almost, and I'm guessing wildly here, but is that outlier line up there at the top, subject 36 by any chance?
This is actually a single subject's data.
That's a single subject
Yeah.
data, okay, so that's.
So that kind of relates to the previous point. There are a lot of outliers. You can actually see
Yeah,
them on this
they're
plot.
a huge number in there. I was just thinking that, was wondering if it would be relatively much easier to impersonate subject 36 than to try to become a woman.
Well, that depends on your gender already.
Yeah, I know, but I'm still, I'm deeply suspicious of things like this based on the size of the sample and the fact that not all women are women in the way things cluster.
Yeah.
But 36 is so much of an outlier that I'm wondering if somebody whose normal typing speeds are fairly fast could actually force themselves to slow down, because I believe the distinguishing feature was fairly large values in a number of the latencies and.
But it's also, I can go back to that. So it's not only that. Let's see if I can find the table here. So it's not only that the latency times are very long. It's also that the hold times are very short. I hope I got that right. Yeah. So it turns out that latency times are fairly easy to control, because these are. So here's the slide I think I wanted. So the 36 is at the bottom of this table. He has very, very fast hold times. And it turns out that, as far as for the little work that we've done in impersonation, latency times are fairly easy to impersonate, right? Especially if they're slow, right? It's hard to impersonate somebody who's really fast, but slow is easy. But to control the hold time is actually quite difficult. It's very difficult for a human to say, okay, I need to generate a hold time of 50 milliseconds and not 55 milliseconds. And it's a time range that we have difficulty in controlling. And so that often, having participated in attempts to impersonate, you have to change up your typing style. And it's quite difficult, I'm not saying it's impossible, but I think it's quite difficult to change your typing style and your key striking style while also maintaining faithful latencies.
We can point out that the average keystroke hold time is around 100 milliseconds.
Yeah.
And just to compare that with something that you're more familiar with, the average time it takes for an eye blink is 250 to 300 milliseconds.
Yeah. And here for 36, we're talking about 50 milliseconds, which is twice as fast.
This is Frank Reitzer again. This is a really interesting study. I know you don't have much time. I'm interested a little bit in the generalizability. Did you say that the same password was used, that string was always that string?
Right.
So in terms of applying this to recognizing an individual, I'm thinking about, like, if you could use a lot of different passwords, of course you have to get more data, and then looking at the transitions between the individual characters, like if it happens to have an A and a T, the transition between the A and the T, or the transition between an X and a 1. And I'm wondering if maybe you could find a little bit more consistency across or within subjects, and the ability to discriminate between different individuals based on those transitions.
Yeah, so that's what you've described is essentially the free text problem. That is, you have different people typing different things. These may not necessarily have overlaps, both in terms of characters and also in terms of diagram pairs. And the hope, of course, is that you would be able to develop such a framework to work on free text. But as far as I know, there's nobody who's really come up with anything that is very general in nature, that addresses this free text problem. People have done fairly crude things like, we'll split the keyboard into 3 sections, right, left, right, and middle, and we'll call transitions between these different sections, right, left, left, middle, middle, right, right, instead of something more detailed like what you're describing, right, to say.
And I'm not really talking about free text, because these passwords are not literally like free text, so you do have some weird transitions. The other thing is on slide 12, that's an individual. Did you say that was their first trial?
Let's see. Slide 12? Yeah. So this is all of the data from a particular subject. It's all 400 repetitions.
Oh, I see. Okay.
So Virginia's next.
You're on the slide, I wanted to ask you
Oh,
that.
great, yeah.
So you said those are all 400 repetitions, are they, so that's just one session though, that's session 8?
No, so this is all 8 sessions. So session, maybe I should have been a bit clearer here. So each session is 50 reps, so imagine kind of half lines here. So the first session is going to be this stuff here on the left, and you can see there's a lot of change. On the last 50 repetitions here, this will be session 8, where you can see the curve is almost flat. So there's no change, really, in the typing behavior of the subject.
So you made a decision to go with most practiced,
Right.
that, assuming that that would be the place that you would be able to best distinguish.
Yeah, so I went with most practice because I didn't want to have a large practice effect kind of influencing the results that I obtained. So if I took all of the data, right, all 400 repetitions, I'm potentially looking at data from up here from a subject with data from down here from the same subject. And that's already quite distinct within the same subject.
So you're assuming that from session 1, you would not be able to distinguish. And so did you try it just to show that you would have?
Yeah, so we did try clustering with each of the sessions, and you can see that in session 1, it's kind of an amorphous blob. Everybody is kind of together in the same cluster. There's not any clearly defined structure. And part of that is because this is a curve for one person. Another person kind of might be down here, another person might be up here, another person might be up here and here. So you have many different curves for many different subjects. And if you just look at the very start of that curve, where they start is almost random in a way. And that makes it very hard to identify structure in the data. Because you haven't yet let everybody get to this point where they're practiced and where they've settled into a particular typing rhythm. And the goal here is to cluster those finalized typing rhythms and not some of the changes that are going on.
Is there some clue in this figure? I mean, it'd be interesting to see this with the figures from the other subjects.
Yeah.
But it looks almost to me as though there's some clue in here about how much practice is enough. That it would be interesting to see whether you got the same results at, say, session 5 or 4 as you got out at session 8, where you've got a slight, almost linear slope in there. You know, how much better does it get as you go from the sessions where it starts to flatten out to the tail?
Yeah. So there's actually work that Roy and I have been doing that's almost written up now that talks just about practice, not in the context of clustering, but just about practice. And I think it depends on what level of change you're willing to tolerate. So if I recall, I think the median point for somebody to have an expected change of about 1 millisecond and how long they take to type a password doesn't occur until about 250 repetitions in. And then it's not to get, if you want a percentage change, I think to get like 0.1% is all the way out at 300 something repetitions. But I'll have to look up those numbers. But you're right. It definitely would be interesting to know, if for no other reason than for future work, how much data do you actually need to collect before you can start doing this analysis? Do you need the full 400, or are you okay with just collecting 250?
Could you turn it around? Could you turn it around and ask the question of, at what point does the clustering fall apart, and does that tell you how much is enough?
I suppose you could. I hadn't thought of that, but yeah, you definitely could. I'd have to think a little bit more carefully about exactly what those criteria would have to be, but it's certainly an idea that can be pursued.
We let Deb have the last question.
Sure. There's one last question, and we're past time for
Oh, I'm
lunch.
sorry.
Thank you. That's my fault.
So that's okay. So the question I have, this will betray my mission-oriented research bias because you're doing a science advancement. When I look at this, my mind says, all right, we've discovered we can do clusters and markers are interesting and you can do a good job of distinguishing among people. I would think through to the next step, which is I'd be unlikely to ever ask our population to type the same password and use the same password to distinguish among themselves. And it'd be difficult for me to gather this amount of data on our entire population with distinct passwords. But what I could do is have a challenge phrase that one would type. And so what I'm wondering is, and I'm not asking you to answer the question, but I'm asking you how you would change your experimental design. If you were to take this set of results, and instead of using this particular database, redesign so that you could determine, is there a sequence of characters, whatever length, that would maximally distinguish amongst a very large population, such that the phrase could be known in advance, and we could then capture similarly to what we do with the retinal scan and so on and so on, and distinguish as a password. So how would you change your research design, and how would that affect the expense that it would take? Because it's clearly very expensive to capture this set of data, which is why I can really relate to why you're doing what you're doing here.
So to make sure I've understood your question correctly, it's really about designing the phrase, right? And kind of
Yes.
working
How
backwards
would you
towards that.
design a phrase to be used for a
Yeah.
very large population? The
So-
phrase is no.
Yeah, so I'll answer a slightly more general question, which is, in keystroke dynamics as a whole, what phrase do you want to use for your experiment? If you want to distinguish people, what phrase is it that you should use? And the difficulty, at least currently, in answering that question and giving a satisfactory answer is we actually know very little about how people type. Because the way the research has gone for the last many years in keystroke dynamics is people say, hey, I'm going to gather some data from over here. All right, I have an algorithm over here. I'll throw the data into the algorithm. I got 83% accuracy. Aren't I great? Right? And then someone else comes along and says, I did the same thing. I get 86. I'm even better. And there's really been very little advancement to say, okay, well, here are the kinds of behaviors that we see. So I can tell you some of the things that I can observe in the data to say, well, there tend to be long pauses between syllables as people type. Well, that's not in the literature anywhere. I probably should make an effort to put it in the literature. But even something very basic like that, which you could have anticipated if you know anything about sort of cognition and chunking and so on and so forth. We just haven't explored that in this field. And I think that's one of the major shortcomings to be able to answer a question like what you've posed, which is perfectly reasonable, to answer that in a satisfactory manner.
I'd like to just respond to 2 points here. One of them is that, while we share that kind of interest, it's quite hard to get that kind of stuff published. Not that we won't try. The other, and to your question about how would you generate challenge phrase, it's some other work that we're doing. We are looking at a problem that's very similar to that. And what we've done is we've generated a large number of candidate phrases, and we put those into mechanical Turk. Right? And based on the results from that, we know certain characteristics of some phrases, which then we can turn around and use in our laboratory research. I can say more about that offline.